All right, here comes the next installment of Yes Prep Calculus videos. In this video, we're going to focus on the unit that we call the integral as a function. This is unit 6 in our scope and sequence. In this unit, we finally will be leaving the graphing calculator. Up until this point, students have looked at definite integrals, but every time we've done it, it has either been using properties of integrals or using the graphing calculator. More often than not, we're using the graphing calculator. In this unit, this is where we're going to hit on integration techniques. Students are going to be expected to basically memorize a lot of integration formulas. And although we take the time to develop them, show why they are true in the calculus course in the video, I'm just going to point out, about a dozen integration formulas that you just have to have memorized. You can find lots of different textbooks that'll take you through why these formulas are the way they are. But we're just going to go over, here's what they are, let's apply them. We'll then do some integration by substitution problems, some that are very much, they're consistent with the level we've done in class, they're consistent with what you're going to see on the AP exam, and also a couple of problems that are going to extend beyond what is likely to be seen on the AP exam. Right? I want to enrich us a little bit. And then we're going to end with the very typical free response question that you should hope to see on the AP exam on Wednesday, May 9th. So let's get into this. At the very start of the unit, we actually are introduced to two kinds of integrals. Up until this unit, the only integral a student has ever seen is called a definite integral. We are used to seeing the integral sign with a lower limit of integration and an upper limit of integration. We're integrating a function with respect to x. And the big question being asked here is usually how much area is bounded by f of x, the x-axis, and the vertical lines x equals a and x equals b. The picture I would want you to have to go along with that, here's my function f of x, here is the vertical line x equals a, here is the vertical line x equals b, and I just want to find all of that area. And for specific ways to go about doing that, you'd want to see the video on Unit 4. We talk about Riemann sums and ways to approximate it. But by this point, this is expected, that when a student sees this notation, they understand that it is a definite integral, and that is different from the new kid on the block, the indefinite integral. And so when we look at an indefinite integral, we are still looking at an integral of a function with respect to a variable, but we no longer have limits of integration. This is the first time students have seen a problem like this. And when we introduce it, we say, okay, well, the final answer is a function. It's big F plus some constant of integration, C. We always refer to C as Charlie, which is a little more loving. But the big question is, what function, big F of x, has little f of x as its derivative? That's what we're after. So, for example, if I said, all right, I want to take the indefinite integral of 3x squared dx. If you think about the big question, the question is, what function do you know of? What function have you come across in calculus that when you take the derivative, you get 3x squared? I picked a nice, easy example here. I would expect that all of my students could instantly tell me it's x cubed, but now here's why it's x cubed plus Charlie. Well, x cubed has a derivative of 3x squared, but so does x cubed plus 1. The derivative of a constant is 0. So does x cubed plus 2. The derivative of x cubed plus 2, 3x squared plus 2. In fact, x cubed plus any constant c is going to be an antiderivative of 3x squared. So we formally refer to c as a constant of integration, Informally, in calculus class, this is just our friend Charlie. And on a regular basis, you'll hear somebody say, "Don't forget about Charlie." All right, so integration formulas that students should have memorized by this point. I would expect that anytime they see x raised to a power, this could be x to the fourth, x to the fifth, x to any power at all. What we know to do at this point is that you add 1 to the power and you divide by the new power. So the indefinite integral of x to the n is 1 over n plus 1, x to the n plus 1 plus Charlie. What we really normally say in class is you add 1 to the exponent and you divide by the new exponent. And that is true except if n is equal to -1, because if n is equal to -1, you would get -1 plus 1, 0 in the denominator, and we can't have 0 in the denominator. So this first one is our general power rule, and it works all the time unless n is equal to -1. Well, let's look at the second one. We have 1 over x as the function. If we ask ourselves the question, what function do I know of that has 1 over x as its derivative? That's something I expect all of my students will know. They'll tell me that the indefinite integral of 1 over x dx is the natural log of the absolute value of x plus Charlie. The absolute value bars are essential. They're essential because what we know about the natural log graph, your natural log looks like this graph over here. You are not allowed to have any negative numbers in the domain of the natural log. So by putting the absolute value bars around the x, you're guaranteeing that whatever value you plug in for x, once you take the absolute values, you will get something that is a positive number, unless, of course, x is 0. All right. So now let's get to ones that some of my kids really struggle with. The indefinite integral of the square root of x dx. At first, when we first came across this caused some problems, but we've gotten pretty good. We know that the square root of x can be rewritten as x to the 1/2 dx. Because this is now x to a power, we're going back to rule number 1 here, we are supposed to add 1 to the exponent, and then we are supposed to divide by the new exponent plus Charlie. 1/2 plus 1, that is going to be x to the 3/2 power. 1 divided by 3/2, we would keep it, change it, flip it, and that becomes 2/3. So your final answer for the antiderivative of the square root of x is 2/3 x to the 3/2 power plus Charlie. Sadly, I didn't give myself nearly enough room there. All right, so now I want to take the indefinite integral of x times the square root of x. I'm going to leave the x alone. Square root of x we know is x to the 1/2. Now let's be careful. There are no properties for when we are multiplying functions together. We have none. So if I have x times x to the 1/2, I am not allowed, I'll say that again, you are not allowed to just find the indefinite integral here, multiply it with the indefinite integral there. Instead, we're going to rely on our algebra skills. X times x to the 1/2 is the same as x to the 3/2 power. Now I have x to a power. And since I have x to a power, we're going to add 1 to the power. 3/2 plus 1 is 5/2. And then you're going to divide by the new power. If I take 1 divided by 5/2, what I really get is 2/5, and then plus Charlie. So the indefinite integral of x times the square root of x dx is 2/5 x to the 5/2 power plus Charlie. All right, most of these are going to be pretty quick. The indefinite integral of e to the t. Ask yourself the question, what function do I know of that has e to the t as its derivative? And the answer is e to the t. The indefinite integral of e to the t is e to the t plus Charlie. Now, what if I have the indefinite integral of e to some constant times t? Imagine that's e to the 3t. Well, if I just say e to the 3t plus Charlie, let's see, does that pass the test? is it true that the derivative of e to the 3t is e to the 3t? Well, if I take the derivative of an exponential, it's e to the same power times the derivative of the power. So I would be multiplying by 3. Since I don't have multiplying by 3 in the integrand, what that means is I need to have a 1/3 here. So the indefinite integral of e to the 3t power is 1/3 e to the 3t plus Charlie. So the indefinite integral of e to the kt dt, assuming that k is a constant, will be e to the kt plus Charlie, and then times 1/k. All right, the indefinite integral for sine of theta d theta. What function has sine as its derivative? If I start with cosine theta, well, let's see if that passes the test. The derivative of the cosine is negative sine. I don't have a negative here. So to compensate for that, I'm going to make it negative cosine. And let's check it. Is it true that the derivative of negative cosine of theta is sine theta? Well, derivative of cosine is negative sine. Then multiply by that negative, I get positive sine theta. There we go. The indefinite integral of sine k theta d theta is going to be, well, let's do it again, negative cosine theta plus Charlie. And then do your check. Would taking the derivative of negative cosine k theta plus Charlie get you back to sine k theta? The derivative of negative cosine is sine. You leave the angle alone, but then you multiply by the derivative of the angle. That gets you a k that you're multiplying by. I don't want that, so I multiply by 1/k. All right, the indefinite integral for cosine of theta is just going to be sine of theta plus Charlie. We know that to be true because if I take the derivative of the sine, we get the cosine. What about the indefinite integral of cosine k theta d theta? Well, that's going to be sine k theta plus Charlie with a 1/k in front. Notice in all three of these examples, I'm integrating e to the kt power, I'm integrating sine of k theta, I'm integrating cosine of k theta, and in all cases, the baby part, in this case the exponent, the angle, that stays the same. But we wind up multiplying by this factor of 1/k. That is always going to happen as long as k is a constant. All right, secant squared of theta. Now, this is one where I'd say maybe 20% of my students have this one memorized. So if you ask the question, what function has secant squared theta as its derivative, we proved it at one point, and some people have it memorized. That's your tangent of theta. So the integral of secant squared theta is tangent theta plus Charlie. The indefinite integral of secant theta tangent theta is secant theta plus Charlie. We're not going to go through proving either one of these. These are just two that some people have them memorized. Great. If you don't, you're probably going to be okay. They don't show up all that often on the AP exam, but I wanted to make sure we were being complete. All right. So, now that we've got the basics under control, here are 3 integration problems. All of these are going to require some fancy algebraic manipulation. So let's just jump into the first one. I want the antiderivative of e to the t plus e to the negative t squared. What I would hope is that my students would say, all right, I need all of this squared, so let me make this e to the t plus e to the negative t, e to the t plus e to the negative t, dt. You know, a popular move at yes is we would make the box e to the t plus e to the negative t, e to the t plus e to the negative t, and now we multiply. E to the t times e to the t is e to the 2t, right? The bases are the same, so you add your exponents. E to the t times e to the negative t, bases are the same, add the exponents, e to the 0. E to the negative t times e to the t, e to the 0. e to the negative t times e to the negative t is e to the negative 2t. What's left in the box is how I'm going to rewrite my integrand. So I have e to the 2t, check. E to the 0 is 1. E to the 0 down here is also 1, so I have e to the 2t plus 2 plus e to the negative 2t dt. We do have a property for integrals that we like to use, which is you can split up an integrand. If it's all addition and subtraction, you can find the integral of e to the 2 dt, plus you find the integral of 2 dt, plus you find the integral of e to the negative 2 dt. Integral of e to the 2t, this is why it's really helpful to have that last form memorized. It's going to be e to the 2t times 1/2. Plus, what is the antiderivative of 2? What function do we know of that when you take the derivative with respect to t, you get 2? That's 2t. Antiderivative of e to the negative 2t is e to the negative 2t divided by negative 2, so really I need to make this minus 1/2 plus Charlie. That one was a little messy, sorry. So the antiderivative is going to be 1/2 e to the 2t plus 2t minus 1/2 e to the negative 2t plus Charlie. Check. Feeling good. All right, moving on. Now I need to take the antiderivative of the square root of x plus x square roots of x plus 1 over the square root of x. What I'm going to do here is I'm going to use my algebra skills. Square root of x is the same thing as x to the 1/2 plus x times x to the 1/2 plus this last one here, 1 over the square root of x is the same thing as saying x to the negative 1/2 power. Well, I think we can clean that up a little bit more, especially over here in the middle. So I'm going to rewrite this as x to the 1/2 power plus x times x to the 1/2 is x to the 3/2 power plus x to the negative 1/2 power dx. Because I have nothing but addition in this problem, I can split it up as 3 integrals. X to the 1/2 plus the integral of x to the 3/2 dx plus the integral of x to the negative 1/2 dx. These are all power rule problems. X to the 1/2, add 1 to the power, that's x to the 3/2. Divide by the new power, divide by 3/2, multiply by 2/3. Plus, integral of x to the 3/2, we add 1 to the power to get 5/2. We divide 1 by 5/2, we get 2/5. Plus, x to the negative 1/2, be careful, negative 1/2 plus 1 is x to the positive 1/2. 1 divided by 1/2 is 2, and then plus Charlie. There we go. Last one for this set. The integral of the sine of 2x plus cosine of 2x. So the antiderivative of sine of 2x is, well, I know it's going to be a cosine. I know there's going to be a 2x there. I know there has to be a 1/2. And now the place where I want to stop and think, the antiderivative of sine, that is negative. So we need negative 1/2 cosine of 2x. Plus, I need the antiderivative of the cosine of 2x. That's pretty easy. That's your sine of 2x with a 1/2 in front there. I almost made that same mistake, which is why it's good to do a check step. Let's take the derivative. Leave the negative half alone. It's a constant that you're multiplying by. The derivative of cosine is negative sine, so I have a negative times a negative will be positive. Sine of 2x times the derivative on the inside, which is 2. That'll cancel out with the 1/2 because 2 times a half is 1. Good. I get the first term. Let's do it again. 1/2. The derivative of sine is cosine. Leave the 2x alone. Times 2. That 2 with the 1/2, that's 1. Check. That's your derivative. Antiderivative. Okay, now we move into the land where we are doing we're doing definite integrals, again, without the calculator. And so the process here, and I forgot to include it in the video, is we're going to first find the antiderivative. So the antiderivative of 8e to the t is 8e to the t, plus the antiderivative of e to the 8t is e to the 8t times 1/8. With a definite integral, remember it's a definite integral because we have these limits of integration. Okay, this makes it a definite integral. What's going to happen is after we perform the integration, instead of writing plus Charlie, we now need to evaluate our antiderivative at -1 and 1. And in order for us to do this, we're going to evaluate the function at 1 first, meaning you are going to replace all the t's with 1. I'm going to get 8e to the first plus 1/8 e to the 8th minus, so I evaluate the function at t equals 1, minus what I get at t equals -1. Let's use parentheses. And that'll give me 8e to the -1 plus 1/8 e to the -8. If you want to clean that up a little bit, you can make this 8e plus e to the 8th over 8 minus, we're going to distribute that negative through, 8 instead of e to the -1, I'm going to send the e to the denominator. Instead of e to the -8, I'm going to send that to the denominator, so I'll have 1 over 8 e to the 8th. And because that minus sign would be distributed, I'd have a negative in front there. And as ugly as that is, that's the final answer. There are no like terms. Nothing's going to cancel. So we're just going to leave it there. Let's move on to the next one. I have another definite integral. So I need to find the definite integral from -2 to 0, 3x minus 9e to the 3x. So in order to do that, we're going to take the antiderivative of 3x, which is 3x squared divided by 2, minus the antiderivative of e to the 3x would be e to the 3x times 1/3. But wait, we've got that 9 there that is multiplying the e to the 3x. So that's actually going to be minus 9/3 e to the 3x. You then evaluate your indefinite integral between -2 and 0. That means we're going to, again, plug in the 0 first. 3 times 0 squared is 0, divided by 2 is 0, minus 9 over 3 is 3e to the 0 power, minus, now we plug in -2. -2 squared is 4 times 3, I get 12, divided by 2, 6, minus, I already said 9 divided by 3 is 3. Now we have e to the 3x power. If x is -2, we're going to get that. We can clean this up a little bit. 0 minus 3e to the 0 is 3, minus 6, plus 3e to the -6 power. I can combine like terms. I have 0 minus 3 is -3, minus 6, -9, plus 3e to the -x. And again, no simplification to be done. If we go to this last one, I want to find the indefinite integral, the definite integral from 0 to pi over 6 of secant theta, tangent theta, d theta. So, if you just know it, what has secant theta, tangent theta as its derivative? That's right. That's going to be secant theta. You now evaluate between 0 and pi over 6. In order to do that, we're going to plug in the pi over 6 first. So secant pi over 6 minus secant of 0. And despite having been a high school math teacher for a really long time, I cannot just tell you off the top of my head what secant of pi over 6 is, but I do know from pre-calculus that secant is 1 over the cosine. So I'm going to rewrite this as 1 over cosine pi over 6 minus 1 over cosine of 0. Now, cosine of pi over 6. Pi over 6 is 30 degrees. Cosine of 30 degrees would be square root of 3 over 2. So I have 1 over square root of 3 over 2 minus 1 over cosine of 0 is 1. If this was if this was the free response part of the AP exam, we could stop. But let's go further. Let's push ourselves here. 1 divided by square root of 3 over 2. That's when we do the keep it, change it, flip it, and we get 2 over the square root of 3 minus 1. If you don't like having a radical in the denominator, which in calculus is fine, but in algebra we tell you not to do that. Don't leave your final answer. You multiply the numerator and the denominator by fancy 1. Multiply by the square root of 3 over the square root of 3. So you get 2 square roots of 3 over 3 minus 1. Even better, if you want to get a common denominator, 2 square roots of 3 minus 3 over 3. Now, before we leave this last problem, I just want to make it really clear. You could have stopped here at this point. These are all numbers. These are all numerical values. You could have even stopped here. No need to multiply by the square root of 3 over the square root of 3. You could have stopped here. No need to get a common denominator. Or you could go all the way and get that final expression. 2 square roots of 3 minus 3 all over 3. You can stop anywhere that I've placed a check mark because these are all numerical answers. Free response part, stop anywhere that you'd like to. But it's the multiple choice that I want to make sure that you're well prepared for. I will never, ever, 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 ever give this to you as one of the multiple choice answers. It's very unlikely I would even give this to you as a multiple choice answer. I don't like square roots in the denominator. I might give this to you as a multiple choice answer, but most likely it's this one. I really want to push everyone's algebraic thinking, their skills and their fluency with fractions and mathematical concepts. So make sure that you are ready to go all the way to a point like this on the multiple choice. But if it's free response and you're pressed for time, you can stop here. All right, let's see what else I've got cooked up. Ooh, wow. Now we come to integration by substitution. This is a topic where I think it challenges you to really think creatively. And, you know, when you first look at this integrand, x e to the 3x squared minus 5, this doesn't fit any of the rules we've looked at so far. I have x times e to the 3x squared minus 5. As I've already mentioned in the video, we have absolutely no properties for what do you do when you're multiplying two functions together and then taking an integral. You have no product rule here. Product rules for derivatives. This is an antiderivative problem. What you're going to have to do is a technique called integration by substitution. In class, this is where we are going to make the problem simpler by replacing a part of the problem with u, and then we'll go from here. So I would expect most of my students, because we've had conversations about, we always refer to u as the baby. This is the same baby from the chain rule back in Unit 3. Where would we see the baby? Where does the baby like to hide? We've established in class that the baby likes to hide in the exponent. We also know that the baby likes to hide underneath radical signs. We know that the baby likes to hide in the denominator. The baby sometimes likes to be the angle, right? That we're always looking for the baby function. In this one, we're just going to jump right in. U is 3x squared minus 5. Just have faith, and I'll show you the next moves. After we've identified that this is u, we're going to take the derivative of u with respect to x, which is 6x. The derivative of 3x squared is 6x. After that, we're going to solve this resulting derivative for dx. I want to get dx by itself, and you're about to see why. I can do my favorite trick from middle school, which is cross multiplying. And I get that du is equal to 6x dx. Again, my goal is solve for dx. So dx is du over 6x. At this point, I have an expression for u. I have a new expression for dx. I'm going to go back to my integrand. We're going to leave the x alone at first. E to the 3x squared minus 5. Since we know 3x squared minus 5 is equal to u, I don't have to write that anymore. I can just call that u. Dx, this expression over here, we know is the same thing as du divided by 6x. Now, my integrand used to have just x's. It now has a combination of x's and u's, and this doesn't look good or feel good at first. But if we pay attention, I've got an x up here with an x in the denominator. Those can cancel out. I have a 6 in the denominator. That 6 is a constant. So I can factor constants out in front of the integral. And I'm going to get 1/6 the integral of e to the u du. This is a much, much easier integration problem to have to do than this original one. They're algebraically equivalent to one another if you replace u with 3x squared minus 5 and you replace the du with 6x dx. So because of this integration by substitution, we now have a really easy problem to solve. The integral of e to the u du is just e to the u plus Charlie. And we replace the u with 3x squared minus 5 because that's what we started with. Now, before anybody just blindly accepts that that is true, yeah, I'm a smart guy, also good looking, I know. Let's actually check it. The check step is, it's a derivative step. If I take the derivative of 1/6 e to the 3x squared minus 5, that's a chain rule. It's going to be 1/6 times e to the 3x squared minus 5 times the derivative of the baby, right? That baby likes to be in the exponent. The derivative of 3x squared is 6x. 1/6 times this times 6x. The 6's can cancel out. I can rewrite this as x e to the 3x squared minus 5. And happy day, that is the integrand that I started with. This is the check that tells me I've done this correctly. All of my work is accurate. I selected the right baby. I've found the right antiderivative. Everything's great. So let's go on to this next example. We can pick up the pace a little bit. I want the integral of cosine of theta over cube root 2 sine theta minus 1. The baby likes to hide in the exponent. Okay, the baby likes to, so let's say, baby likes to hide in the exponent. The baby likes to hide under radical signs. The baby likes to hide as the angle in a sine or a cosine. The baby likes to hide inside the absolute value bars of the natural log. The baby likes to hide in the denominator of a fraction. So we've got a couple of choices here. I'm going to select 2 sine theta minus 1 as the baby. I take the derivative. Before it was with respect to x. Here theta is my variable, so we'll say du d theta. And that's going to be 2 cosine of theta. We're going to solve for d theta, which again can be a cross multiplication if you see it that way. D theta times 2 cosine theta is du. So that means that d theta is du over 2 cosine theta. At this point, we take our original substitution and the d theta, and we rewrite our integrand. We don't have a new way to write cosine of theta, but you're going to see it's okay. Instead of the cube root of 2 sine theta minus 1, I'm going to write it as the cube root of theta. Instead of multiplying by d theta, I'm going to multiply by du over 2 cosine of theta. I bet you're starting to see it. The cosine theta and the cosine theta are going to cancel out. Let me clean this up a little bit. So now I have 1 over the cube root of u times du over 2. That 2 is a constant. I can pull it out front. So 1/2 times indefinite integral 1 over the cube root of u du. This is kind of ugly, but I have some good algebra skills That reminds me that 1 over the cubed root of u is the same thing as u to the negative 1/3 du. I have a power of u. That is good, because now we're going to use the general power rule, which says you add 1 to the power, negative 1/3 plus 1 is 2/3, and then you divide by 2/3. That is the same thing as multiplying by 3/2 plus Charlie. 1/2 times 3/2 is 3/4. U to the 2/3 plus Charlie. And finally, before you congratulate yourself too much, let's keep in mind that the original integrand was in terms of theta. I cannot leave my answer in terms of u. So my final move is going to be 3/4 times 2 sine theta minus 1 to the 2/3 power plus Charlie. That is our final answer for that integral. I'm not going to bother doing the check step, but you can do the check step yourself. Use a chain rule, right? Take the derivative. Convince yourself that you actually get this expression back. If you do, then you know beyond a shadow of a doubt that this is the correct answer. If you're not getting this integrand as your answer, then a mistake has been made. All right, we've got 2 more integration by substitution problems. Now, before we get too excited about this being integration by substitution, I want to pay careful attention to the fact that I actually have limits of integration. And if you're a student at East End or Southwest, I'm just going to publicly out myself. I was sloppy with my notation, and I allowed you to get away with some bad mathematics. We were all ultimately arriving at the correct final answer, so that's a good thing. That's a really good thing. But I let some sloppiness occur with the notation. So I'm going to do this problem once, the way we've been doing it in class, and then secondly, I'm going to do it again. I'm going to point out what my mistake is and promise to hold everybody to higher standards. We've had our tribute to Star Wars. Thank you, Bells at East End. Let's do this. Okay, the baby, x squared plus 1. We take the derivative of the baby. We get 2x. We're going to solve it for dx, and dx is going to be du over 2x. Now, here's the sloppiness. We would rewrite the integrand and say it's x over, instead of x squared plus 1 cubed, u to the 3rd. We'd rewrite the dx as du over 2x. We cancel out the x's. We have a 2 in the denominator, so we get 1/2 integral of 1 over u cubed du. And the sloppiness comes in here. We've changed our integral from being in terms of x's to being in terms of u. These limits of integration, the 0 and the 1, are x values. And so what I was allowing to happen is students would just continue writing that 0 and the 1 all the way through the problem. They would finish this off. They'd say, all right, well, let me rewrite 1 over u cubed as u to the negative 3rd du, again, using 0 and 1. U to the negative 3rd, I'm going to integrate as add 1 to the power, so it's u to the negative 2, times 1 over negative 2. Because it's a definite integral, we're just going to go from 0 to 1. I could even rewrite this. 1/2 times negative 1/2 is negative 1/4. That u to the negative 2 I can send downstairs as u squared. I'm going to evaluate this between 0 and 1. But stop, wait, hold on a minute. These are x values. We cannot plug in these x values into u and expect to get the right answer. So you replace this at this final step before you plug in. You rewrite the u as x squared plus 1 squared. And now you evaluate it between 0 and 1. If I plug in the 1 for x, I'm going to get negative 1 over 4. See, we're plugging in 1. 1 squared is 1, plus 1 is 2. 2 squared is 4, minus. Now evaluate that function at 0. You're going to get negative 1 over 4. 0 squared is 0, plus 1 is 1. 1 squared is 1. That gets you to negative 1 over 16, plus 1/4. If you get a common denominator, that becomes 4/16, and you get 3/16 as your final answer. And that is the correct final answer. And you should be really proud if you made it to 3 over 16. And a lot of my kids made a lot of progress, and we're getting to 3 over 16. We're high-fiving one another. We're happy, happy people. But the technicality comes in, again, with these limits of integration. Unless you're going to write at every single step, x equals, x equals, x equals 1, x equals 0, x equals 0, x equals 1. Unless you're going to actually write that at every single step, there's a possibility of you're losing some points. And nobody wants to lose any points. So method number 2, and this is not one that I modeled in class. So we would do the same substitution. We're going to select u as x squared plus 1. We're going to take the derivative, and we're going to solve it for dx. But when we get to the point of rewriting the integrand, x over u cubed du over 2x, we know the x's cancel out. We know we get to 1/2 the integral of 1 over u cubed du. Because the integrand is all in terms of u, our limits of integration need to be in terms of u. I'm going to say that again. Because the integrand is in terms of u, we need our limits of integration to be in terms of u. So, let's see. We started off with x equals 0 as the lower limit. We have this relationship that u is equal to x squared plus 1. So that means that u is equal to 0 squared plus 1. So my lower limit of integration is going to be u is equal to 1. Now let's look at our upper limit. We used to refer to the upper limit as x equals 1. If x equals 1, then u is 1 squared plus 1. U is 2. From now on, I can just write 1 and 2 as my new limits of integration. I'm going to finish this problem off. So we'll get 1/2. We're evaluating between 1 and 2. These are u values. U to the negative third du. We get to the same, add 1 to the power, u to the negative 2, divide by negative 2, evaluated between 1 and 2. And I can simplify it to negative 1 over 4u squared. Now I'm evaluating between 1 and 2. Because these are limits of integration, these limits of integration are in terms of u, and my antiderivative is in terms of u, I'm just going to plug them in directly. And I get negative 1 over, plug in the 2, 4 times 4, minus negative 1 over 4 times 1. I get negative 1 over 16 plus 1/4. Hey, we've seen that before. That's 3/16. We get exactly the same answer. This is a math class. One problem, we want one answer. We get 3/16 both times. The issue is the messiness, the sloppiness in notation that I allowed. We get to 3 over 16. Technically, you should change your limits of integration so that you've gone from x's to u's, and you just end the problem with u. If you don't like this new method, then my request for my students is, when you're doing integration by substitution, keep writing x equals next to your limits of integration, x equals, all the way through. At the end, you convert your antiderivative back to x's, and then you evaluate it. And that's going to be okay. All right, let's do one more integration by substitution. This one's an especially tricky one because it does not follow our pattern for where the baby likes to hide. We always talk about the baby. The baby likes to hide in the exponent, in the denominator, it's the angle, it's blah, 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 blah. You might select u as x times the natural log of x. Well, if we do that, then du dx is going to be a product rule, and so it'll be 1 times the natural log of x plus x times 1 over x. You get natural log of x plus 1. You would get that dx is du over the natural log of x plus 1. If you were to actually go back and rewrite your integrand, try to do that in terms of u, you're going to see that things are not going to cancel out in the way that you like them to. So, I know that was kind of quick and dirty, but that's not the right substitution to do. Instead, we're going to let u be the natural log of x. I'm only taking part of the denominator, and you're going to see what happens. If u is the natural log of x, then du dx is 1 over x. When we cross multiply, you'll get that dx is equal to x times du. Go back to your integrand. We're going to write this as dx over x. We know that the natural log of x is u. Because I'm in the process of rewriting my limits of, my integrand in terms of u, I change my limits of integration. If x is equal to e, then u is the natural log of e. The natural log of e is 1. My upper limit, x equals e squared. When I do that down here, I get u equals the natural log of e squared. The natural log of e squared is 2. What I forgot to do is I forgot to finish rewriting my integrand. I have x's and u's mixed together. Fortunately, we know that dx is x times du. We have xu in the bottom. The x's cancel out. I have the integral from 1 to 2 of du over u, which is the same thing as writing the integral from 1 to 2 of 1 over u du. The antiderivative of 1 over u is natural log of the absolute value of u, and you go from 1 to 2. Now, I know my students are going to be tempted. They're going to say, wait, Mr. D, we need to rewrite the u as the natural log of x. Because I changed my limits of integration so that these are now u values, we don't have to do that part. So you just replace the replace the u with 2, and you're going to get the natural log of 2, since that's a positive number, no absolute value is needed, minus the natural log of 1. The natural log of 2 is about 0.693, but let's just write natural log of 2. Natural log of 1 is known to be 0. Our final answer is the natural log of 2. For any of my students that don't like this more proper technique of changing your limits of integration from x's to u's, I would ask you to go and actually do this problem the way that you know how, selecting u as the natural log of x. When you get to the evaluation point, make sure that you change your antiderivative back to x's, plug these in. I promise you, you're going to get natural log of 2 as the answer. It's a slightly revised technique to get you to the exact same answer. Okay, now we have 2 trickier integration by substitution problems. If you're a student in my class, if you're worried about the reassessment next Wednesday, feel free to skip past this part of the video. This is definitely meant to be more of an enrichment activity. So, if we go with the usual substitution, if we say that u is equal to y plus 1, because that's under a radical, and that's a place where the baby likes to hide, I would then say du dy is equal to 1, and I would rewrite that and say that dy is equal to du. When I go up here, I've got y. Instead of square root of y plus 1, I'm going to write the square root of u. Instead of dy, I've got du. Now, that may not at first glance seem to be a problem, but there is a problem here. We started off live, my integrand was all in terms of y. Now I've got this combination of u's and y's, and that's always a sign that you've done something wrong. We want the integrand to be in terms of one variable only. Having a y and a u, that's not going to work. So, and this is something that's not happened in any of the ones we've done in class. This guy over here, the y, we need to remove the y. We need to rewrite it in terms of u. And that's where I want to draw your attention over here. We know that u is equal to y plus 1. With some algebraic manipulation, you can then say that y is equal to u minus 1. That allows you to rewrite your integrand as u minus 1 times the square root of u du. That's all in terms of u. That's a good thing. So we'll have u minus 1 times u to the 1/2 du. I've got u times u to the 1/2 minus 1 times u to the 1/2. All of that du. And so we've got u to the 3/2 minus u to the 1/2. Oh my gosh. Okay. The antiderivative of u to the 3/2, we are going to add 1 to the power. So u to the 5/2 times 2/5 minus antiderivative of u to the 1/2 is u to the 3/2 times 2/3 plus Charlie. Don't stop yet. You're not done. The original integrand was in terms of y. Your final answer cannot be in terms of u. So our final answer will be 2/5 y plus 1 to the 5/2 power minus 2/3 y plus 1 to the 3/2 power plus Charlie. There it is. That's one of those trickier integration by substitution problems that I chose to not do because I knew it was just going to add a little bit of confusion. But I figure in the video it's a great opportunity for enrichment as well. All right, let's look at this last one, and then we're going to move on. Okay, looking for that baby. I'm going to say that u is equal to x minus 2. Baby likes to hide underneath the radical. Du dx is 1, so dx is equal to du. I'm going to go over here and rewrite my integral. I have x squared over the square root of u. Instead of dx, we know that's du. That's a d. Now I have to get x squared out of there. I've got to rewrite this in terms of u. Well, we know that u is equal to x minus 2. So that must mean that x equals u plus 2. If I want x squared, I'm going to square the left and I'm going to square the right. And u plus 2 squared, if I build a box or I just multiply this out in my head, I get u squared plus 4u plus 4. I can then go back to my integral, and instead of x squared, I'm going to write in this expression, u squared plus 4u plus 4 over the square root of u. I'm going to rewrite this, u squared plus 4u plus 4 over u to the 1/2. I'm going to split this up, u squared over u to the 1/2 plus 4u over u to the 1/2 plus 4 over u to the 1/2, all of that du. And technically I should have had a du up there. U squared divided by u to the 1/2, the bases are the same. We keep the base, subtract the exponents. 2 minus 1/2, 3/2, plus 4, u divided by u to the 1/2. Again, subtract the exponents. Plus 4, u to the 1/2 in the denominator is the same as u to the negative 1/2. I still have to take the antiderivative. We're going to go through u to the 3/2, add 1 to the power, that's u to the 5/2, times 2/5, plus 4 times u to the 1/2, add 1 to the power, divide by the new power, plus 4 times u to the negative 1/2, add 1 to the power, divide by the new power, plus c. We've got 2/5 u to the 5/2 power. 4 times 2/3 is 8/3 u to the 3/2 power. 4 times 2, 8 u to the 1/2 power plus c. Ooh, I'm off the screen. So that last line was 2/5 u to the 5/2 power plus 8/3 u to the 3/2 power plus 8u to the 1/2 power plus c. Go back, rewrite all of your u's in terms of x, and you are going to get 2/5 x minus 2 to the 5/2 power plus 8/3 x minus 2 to the 3/2 power plus 8 times x minus 2 to the 1/2 power plus c. Woo! Oh, I love calculus. Look at all that beautiful mathematics that just happened. But there it is. That is integration by substitution. You've got 5 or 6 examples to look at, to consider when you are studying for the test. Good luck with integration by substitution. Okay. We've got an application problem that, because the video is running a little bit long, I'm going to talk you through. I'll kind of just move you in the right direction, but I'm not actually going to go through this step by step. I'll just leave this as an enrichment opportunity for anybody who's interested. This came from Rogowski's calculus book. This is one of my favorite texts this year. It's got some really creative problems. They're well aligned to the AP exam. So here it comes. Wind engineers have found that wind speed, V, which is measured in meters per second, at a given location follows a Rayleigh distribution of the type W of V. So W is a function of the wind velocity. 1 over 32 V e to the negative V squared over 64. By evaluating the integral expression, that's a definite integral from A to B, W of V dV, you can determine the probability that the wind velocity will be between A meters per second and B meters per second. So what they're saying is that this integral expression over here tells you the probability that the wind will be between this lower limit of integration and that upper limit of integration. Using this information, determine the probability that the wind velocity will be between 0 meters per second and 8 meters per second. So what I would have to do is I'm going to find a definite integral of 1 over 32 V e to the negative V squared over 64 from 0 to 8 dV. In order to calculate this definite integral, I know some of you are going to be tempted to get your graphing calculator. Try integration by substitution. Let this guy here, the negative V squared over 64, let that be the U. What you're going to find pretty quickly, once you select that as the U, once you take the derivative, once you solve it for dV, a lot of the stuff is going to cancel out, leaving you a much, much easier integral. And then you evaluate it between 0 and 8, and you're done. So for any of my calculus students, if you want to finish that problem off, bring it in. If you're at Southwest, I'll give you a Beast Point. If you're at East End, I'll figure out what to do. Something nice. I don't know. Lifesavers. Okay, before we formally conclude this part of the video, and I start on the second one, we need to talk about the second fundamental theorem of calculus. This is a big result. The second fundamental theorem of calculus states that if big F of x is defined to be the definite integral from A, where A is a constant, to x, where x is a variable, of a function with respect to t, and A is a constant, F is continuous, then if I take the derivative of big F, that means if I take the derivative of an antiderivative of a function, what I'm going to get is the function back, the integrand function back, evaluated at the variable x. I'm going to say that again. If I start with a function that is known to be the integral, the definite integral from a constant up to a variable x of a function, and this guy here is continuous, so that the pieces to check: is your integrand a continuous function? And generally at this point in calculus, almost all the ones we're going to look at are continuous. The lower limit of integration is a constant, and our upper limit is the variable x. then if all of those are met, if I'm taking the derivative of an indefinite integral, what I'm going to get is f of x. And we'll actually go through and I'll show you an example and you'll say, oh, that's all? Basically, it looks like these two cancel out. For our purposes, I think that's okay. There's also the extended second fundamental theorem of calculus that says if instead of going from a constant up to something a little more complicated, you have a function, something more interesting than just x. Again, as long as f of t is continuous, the added restriction is that the g of x, this function up here, is differentiable, so the derivative exists. Then the derivative of the integral, going from a constant up to a variable, will be f, this guy over here, evaluated at the upper limit, times the derivative of your upper limit of integration. So the derivative of an integral, going from a constant up to some function, this is some function g of x, will be, you take that g of x and you plug it in. F of g of x times the derivative. That's your extended second fundamental theorem of calculus. At this point in calculus, we don't use this one all that much. But we do use the second fundamental theorem of calculus on a very regular basis. So I want to provide everybody with some evidence that I'm not just making this up. If I apply the second fundamental theorem of calculus, which I can, I have the derivative of an integral from a constant up to x. The final answer is just x to the fifth minus 9x cubed. Happy day. That took about 2 seconds to do all that work. That's thanks to your second fundamental theorem of calculus. I don't think that's a well-known abbreviation. Second fundamental theorem of calculus tells me that that's true. But let's pretend I didn't know that. You know, that would be sad. Okay, I would need to take the derivative of this integral. Let's do it. T to the fifth minus 9t cubed dt. Well, I don't know the second fundamental theorem of calculus. So all that's left at my disposal is take the integral of t to the fifth minus 9t cubed. Fortunately, that's relatively easy. You add 1 to the power. You divide by the new power. Minus 9t cubed. I make that t to the fourth over 4. I evaluate this function between 0 and x. After I've done that, I take a derivative. Well, let's do it. I said I have to evaluate the function at x. That'll give me x to the sixth over 6 minus 9x to the fourth over 4 minus, let's see, we plug in 0. 0 to the sixth is 0 over 6, 0. Minus 9 times 0 to the fourth, 0 over 4, 0. Now I take the derivative. The derivative of x to the sixth over 6, that is going to be 6x to the fifth over 6 minus 9x to the fourth. Let's see, I would make that 36x cubed over 4. I can simplify that, and I'm going to get x to the fifth minus 9x cubed. It is exactly what we knew. Thank you, second fundamental theorem of calculus. So you can either know the second fundamental theorem of calculus and spend 2 seconds on this problem, or you can go through life not knowing the second fundamental theorem of calculus. And the next time you come across a problem where you're asked to take the derivative of an integral, going from a constant to a variable of a continuous function, you can go through all this work, and while you're doing that, your friends are 4 problems ahead of you, earning lots of points in the AP exam. Bottom line, know your second fundamental theorem of calculus. Okay, this example down here is, let's see, we have the derivative of an integral. Good. Constant at the bottom. Uh-oh, I've got something a little more complicated here. I don't have just a variable, I have a function. No sweat, we know what to do. According to the extended second fundamental theorem of calculus, you plug that function into the integrand. That'll give you x squared minus 1 to the fifth power minus 9 times x squared minus 1 cubed You then take all of that times the derivative of x squared minus 1, which is 2x. So even in an ugly problem like this, taking the derivative, not so bad. Okay. Here are a couple of other ones that are going to require a little bit of attention. I have the derivative of an integral. That's good. But my constant is the upper limit of integration. My function is the lower limit of integration. They're in the wrong place. That's not a mistake on my part. This is an opportunity to pay a little bit closer attention. What you need to do is you need to rewrite this. You can switch your limits of integration so that they're in the order that you'd like for them to be. But there is a cost for that. When you switch your limits of integration, you introduce a negative into the problem. So now I have negative derivative of an integral from a constant up to a function. You know what to do. It's going to be negative of x squared over x squared plus 1 times the derivative of x squared, which is 2x. There it is. That's your final answer. Unless you're asked to do more, I would stop. Okay, not sure what's happening with that x squared floating out in space. Next one, derivative of an integral, constant, up to a function. Okay, great. That's just, again, your extended second fundamental theorem of calculus. So we make it cosine cubed of 1 over x times the derivative of that function up there, negative 1 over x squared. How fast was that? All right, this one here, we're going to want to slow the roll a little bit. I've got a second derivative, d squared over dx squared. That means I want to take the derivative of a derivative. Let's write that out. I want the derivative of a derivative of this integral, negative pi to cosine of x, u to the 4th du. You can use your extended second fundamental theorem of calculus here for the part inside the parentheses. Derivative, integral, constant, function. We know what to do here. We make it cosine of x to the 4th times the derivative, which is negative sine of x. But that's just the part inside this parentheses. I then have to take a derivative. Well, the good news is I no longer have an integral in here. I just need to take the derivative of the product cosine x to the 4th and negative sine. Way back when, we were really good at this. This is a skill I expect that we've mastered. It's the product rule, right? Inside there, that's just a product rule problem. So let's do the product rule quickly. We take the derivative of cosine of x to the 4th. 4 times cosine of x to the 3rd times negative sine of x. I just had to use the product rule. I'm sorry, chain rule. That's the derivative of the first part. Leave the second part alone. Plus, now you leave the first one alone. Cosine of x to the 4th times the derivative of negative sine, negative cosine. And at this point, because this video is getting much longer than I expected, I want to just end it right there. You could simplify it if you want to. I see negative sine and negative sine becoming sine squared. I see cosine of the 4th times negative cosine of x becomes negative cosine of the 5th power. But that goes beyond what I'm really interested in this problem. I wanted to make sure that we paid special attention. This d squared over dx squared needs to take a second derivative. All right, so with that, that concludes the skills, theorems, and properties part of the video. I'm going to take a little break. The next part of the video, we're going to look at one free response question, which brings in a lot of the big ideas. We're going to focus on our notation and our justifications, and we're going to call it a day.